Okay, so were there any questions on the homework assignment? Which one? 49. Where is everybody today? A little holiday, huh? Our next exam is a week from today. So hopefully we'll have some time to review a little bit next class, and then you'll have the weekend to get ready. All right. Number 49 off of 12.2. I'm being asked about this question here for the homework. X minus 2, then x squared minus 4x minus 8. Is this the one?
Yes.
Okay, so it says, so are you concerned about the sketching, or is that your, because remember I did say at the end not to sketch, right? I said don't sketch. Yeah. Now you would still be responsible for knowing how to figure out where this function is going up, where it's going down, where it's concave up and where it's concave down. So we can still do that if you want. Y'all want to go through that? Yes? Okay. So how do we go about trying to figure out where a function goes up and down? Increasing and decreasing. What do we need to do?
Will we first do like a whole process of folding it? Are you talking about up? Would just be a prime number.
Yeah, so we need to look at the first derivative, right?
Yeah, and then the second one if you want to figure out.
Concave up, concave down. So we need to be able to take both the first and second derivatives of this function. So how do we take the first derivative of this? Because we have this times this, right? You could do the product rule, or you could expand it all out and then take the derivative. It's really up to you. Okay? It really is up to you. I'm going to do the product rule because that was the first thing that was mentioned. So if I do the product rule here, I have to take derivative of this one first, right? Which is what? Just 1, and then times this. So I'm just going to write down x squared minus 4x minus 8. Understand? That's f prime, or sorry, that's this one, derivative of this times this. And then I say plus, now the product rule says we take derivative of this. What's derivative of this piece?
2x minus 1.
2x minus 4, and we need to put that in parentheses because we're going to now multiply that times what? The first function, x minus 2. So that's our first derivative. It's not very nice to look at, but that's what it is. Agreed? Now, in order for me to try and, I'm going to have to set this thing equal to 0, aren't I?
Yep.
So to do that, I'm going to multiply this out first. So I'm going to FOIL this out. Okay, so let me do that. Okay, so what happens here? I get 2x times x, 2x squared, 2x times that, minus 4x inside, minus 4x again, and then finally plus 8, right? Now let's collect all of our like terms together, everything that has the same variable to the same power. So x squared here, 2x squared there. So that's a total of 3 of them, 3x squared. And then how about our x's?
Minus 12x.
Minus 12x.
And then nothing.
And then the 8's cancel. So at the end of the day, that's not really that bad as far as a derivative is concerned, right? So that's our first derivative. Let me go ahead and box this up. Okay, and now we are going to need the second derivative also, aren't we? So let's go ahead and do that now. And luckily for us, the second derivative is not as bad as the first derivative was. 6x minus 12. So there are our first and second derivatives. Okay, now, to figure out where our function is going up and down, right, where it goes up and where it goes down, we need to take the first derivative set it equal to 0, which means I'm going to set 3x squared minus 12x equal to 0. And what can I do with this to try and solve that?
You can divide, wait, no, wait. You can remove the
Factor
Out the x.
a 3x. How about that? 3x. And we'll be left with x minus 4. And now we set each of these factors equal to 0. So 3x equals 0, x minus 4 equals 0, and we have to solve both of those equations. So first one is 0, and the other one is 4. Okay? Now, what do I do with that? Those are my critical numbers, right? So what do I do with them? No plug in, nope. Number line. So now comes the number line, okay? So the number line comes next, and you put these 2 points on your number line, 0 and 4. Make sure they're in the correct order, right? 0 goes before 4. And that will break up our number line into how many sections? 3. And so now what?
Choose 3 numbers.
Choose 3 numbers, 1 in each section. So any number that you can come up with that's to the left of 0. Negative 1. 2. 5. Those work, right? Someone else could have used 1. Someone else could use 6. It's up to you. Those numbers you have the freedom to choose. Now, where do those numbers get plugged in? First derivative, right? Into the first derivative. So we plug them into this, and all we are concerned about is whether or not we're going to get a positive or a negative answer. Okay, so let's try plugging negative 1 in. So I'm going to do this right here. Plugging into the derivative, negative 1, then plugging into the derivative 2, and plugging into the derivative 5. So I'll plug it into this, right? So 3 times negative 1 squared minus 12 times negative 1. Be careful with that minus 12 times negative 1. That's going to become what there at the end? This will be plus 12, right? Okay, and then negative 1, when you square it, it's just 1. So you're going to have 3 times 1, which is 3, and then plus 12, and that's 15. I don't really even care that the number's 15. I just care that it's a positive number. And that tells me that over here, when I plugged in negative 1, the derivative was positive, which means the original function is going up. Now plug in 2. You get negative 12? Okay, negative 12. We're trusting Brian there. Brian? Was that Brian? Brian? Okay. That means the function goes down here. And then you have to plug in 5. You get another positive number. So I'm not going to show those steps, but is that okay? You understand what I'm doing with these? Everyone clear? Okay. So our function goes up, then down, then up. So I want to skip some of this because this is homework. Do we have a local maximum? Yes. Where is it? At 0, right? So to get the actual maximum, we would plug 0 into what? Original. If we want to actually know what the function's height is, we have to plug 0 into this, right? Now, do we have a local minimum? Yes, it happens at 4, right? To figure out the minimum, we'd plug 4 into this and get the answer.
Product rule, right?
Well, no, you're just plugging the number in. We're not doing another derivative, right? So plug 0 into this. I would get negative 2. Then over here I get negative 8 because these would go away. So negative 2 times negative 8 would give me 16.
That's
Okay?
the answer, 16.
For the local maximum would be 16. Yes. Okay, now, what we've figured out where the function goes up and down, all that stuff. Local max, local min, we're done. What's next? Figure out where it's concave up and concave down. So that's different, right? Up, down is different than concave up, concave down. Concave up and down has to do with the shape of the graph. So to work on the shape of the graph, I need to look at the second derivative and set it equal to 0. And just do the basically the same thing, right? Okay, so second derivative equal to 0 means all I have to do is set 6x minus 12 equal to 0. And there's really not a whole lot we have to do with that, right? Just move the 12 over. Divide by 6, we should get 2. What now? Number line? We only have 1 point to put there, right? That breaks up our number line into 2 regions, right? We picked 2 points, 1 on each side. So I heard 1 and 3. Everyone agree we could use those? Where do those get plugged into? To this second derivative, because you're looking at concavity now. So I want to now find out what's f double prime of 1, what's f double prime of 3. So plugging these in to this one. So what happens if I plug in 1 here? I get -6. What happens if I plug in 3? 6. Okay, so all I care about is the positive and negative, right? So at 1, my second derivative is negative. What does that tell me about my original function? What is it doing over here? Concave down, right? Negative people frown, right? Positive people smile. So positive, which means my original function goes up here. Is concave up here. What do we call that point where you have a function that switches from concave down to concave up?
The critical point.
It is a critical point, but with, yeah, inflection, good. It's called the inflection point. So we actually do have an inflection point here, right? It happens at 2. Right? Okay. All right, that's pretty much what we've done up to this point, right? We've got, if someone gives us a function, we can find local maxes and local minimums. Agreed? Okay. So we're going to move on to some new stuff today. I am going to do one word problem before we get to the new stuff, though. Again, our test is a week from today. So, bless you. All right, so let's say that we have a company, all right, and we have this we're given a price-demand equation for our company is P equals, let's go 1,300 minus 0.15 x squared. As long as zeros between, as long as x is between 0 and, let's say, 70. So here P is the price in dollars per unit. And X is the demand. So this is what we call a price-demand equation. We've looked at this in the past. This somehow gives a relationship between what we're going to set the price for this product to be if our demand is X. All right? So if we have no demand for this product, what's our price going to be? What's our price going to be if our demand is if we have no demand? $1,300, right? So if the demand is X, if nobody wants our product, our price is going to be $1,300. We're going to assume that at least one person wants our product and less than 70. All right? That's the assumption here. So this is the question. Find R of X and its local max and local mins. Okay? Now what does R of X stand for? Revenue. Okay? So if we have a price-demand equation, if that's ever given to us, then what is revenue? So this is the question. This is what we're going to answer, all right? So what is the revenue by definition? It's the amount of money coming in, right?
Coming in from sales.
And that's going to be the number of units that we sell times the price per unit. Agreed?
Yeah.
So this is going to be equal to the number of units that we sell, which is X. That's the demand, right? How many people want our product? Times the price that we set for each one. But if price is this, then this becomes X times 1,300 minus 0.15 X squared. Do y'all agree with that?
Yes.
And that, if we multiply that X through here, we have a nice revenue function. So I'm going to write it like this. Revenue as a function of X is equal to 1,300X minus what? 0.15X cubed, right? Cubed. So that's our revenue function. I would like to know where we might have any local maximums or minimums on that, right? That's what I'd like to know. So now we go back to like the homework problem I was just asked about. We have a function. We were trying to find where it went up and down. So how would I figure out where this function goes up and down? Take the derivative, which would be 1,300 minus 0.45 x squared. So derivative of 1,300x, 1,300 comes for the ride, derivative of x is 1. So that becomes that. On this, the 3 comes out front. You have to multiply 0.15 times 3, which gives you 0.45. It's still negative, and then the power comes down. So are we okay on that? Sure?
Yeah.
Okay, now, what do you do after you take the derivative?
Go to 0.
Set it to 0. Okay, so now take my derivative, set it to 0, which means I want to take 1,300 minus 0.45x squared, set it equal to 0. Now I'm going to need someone to help me out with the calculator. I loaned my calculator out to one of my students the other day, and they took it home with them. No, it's okay. I want you to do it. Okay, so
Just move the minus 1.5.
yeah, because there's only 2 terms here, I can just move this one to the other side. Okay, that makes it a positive term, right, when I move it to the other side. Now what?
Why not move the 1,300?
You could do the 1,300 to the other side. It would just become negative, right? So you'd have negatives on both sides, which is fine. You'll get the same answer. In fact, I'll show you. If you did it the other way, you would have had negative 0.45 x squared equals negative 1,300. That's what you would have had, right? Okay, I'll show you that they give you the same answer. What would I do here? I'm trying to solve for x. Divide by this, right? And then divide this side by the same thing, 0.45. So I need someone on their calculator to do 1,300 divided by 0.45. 2,000?
2,000 by 188.88.
88.88, something like that?
88889.
Okay, good enough. 2,888.88 equals what? X squared. Now, if you would have done this instead, you would have divided both sides by negative 0.45 to make negative over negative positive, and then here negative 0.045, whatever. And a negative over negative would be positive. You get the same answer, okay? All right, now, how do I get x? If x squared is this, how do I get x? Square root both sides. So I need, on my calculator, take the square root of 2888.88, which is, what do you got? 53.75. Close enough, okay? 53.75. Okay. Now what?
Now we gotta do a number line.
So that's a critical number, right? So now we need the test point, so we need a number line at this point. Remember, all we want to know is anywhere where we might have local maximums or minimums. Why am I concerned about that? This is my company, right? My revenue is important. It would be nice if I could figure out where I have a maximum revenue, right? Okay, so this is going to allow me to determine whether or not I do. Okay, so now Number line, 53.75. Split it up, pick 2 points. 50, right? 50 will work. And 55 will work. And where do those get plugged in? First derivative, right? Those get plugged into this one right here. Right here. All right, so again, I need someone to do this for me. I need you to square 50 and then multiply times that and then subtract it from that. And tell me if you get a positive or a negative. You should get positive.
1,100.
So it's positive?
Yeah.
Okay. So are y'all okay with me actually letting you handle that computation or no?
I have a question, sir.
Yes.
For that one right there for the derivative, why, I was busy writing this down. So
Yeah, yeah.
I didn't really pay attention to what you were, I forgot the derivative part, and we're trying to find equal to 0. But why is, it split in the middle? Down,
He's just showing that depending on how you equaled it,
Oh,
which side
yeah.
you put, the answer would be the same.
Yeah, one of your classmates was asking, you know, we decided to move this over to this side to get this, but someone asked, could we have moved the 1300 on this side? And I said, yes, you could do it either way, you'll get the same result. Yeah, sorry about that. Don't worry about that. Okay, so plugging 50 into the first derivative, we get a positive answer, right? And what does that tell me about my revenue function over here? It's increasing, right? Okay, and now we plug 55 in to the derivative. And you do all that, and do you get a negative? You should get a negative. And that means my revenue is going down. What does that mean?
It means that it makes more than 53.75.
Well, I'm not losing money necessarily. It's just my revenue is not as high as it would be if I were here, right? So if basically my revenue function looks like this. This is my demand, right? X is the demand. This is my revenue. Here's 53.75. I know that my revenue goes up and then it comes down. That's what I know, right? So if my demand is less than 53.75, I'm going to make money, but not as much as if I was exactly 53.75, right? That would be the maximum revenue. Agreed? Now, you can't have a demand of 53.75, can you?
How are you getting a negative from 55?
I didn't.
It's actually a higher number. It's still a positive.
It's still positive? Should get negative.
we plug in the 55 in the derivative function or the regular function?
55 goes into this.
Okay.
So 55 squared here?
Oh, I got it, minus 16.
You're good? Okay. Now,
Yeah, minus 61.
I didn't.
Oh, okay.
the way, just so you know, the way that I did it, okay, the way that I did it is I said, look, we could pick any number to the left of this, right? 50 was the first number I heard. But what I did real quick is I went all the way back to 1 in my head because 1 is easy to plug in right here. Look, if I plug in 1 right there, that's just 1, right? Then look, 3,000 minus that, that's a positive number. Agreed? Okay. Now, instead of plugging in 55, in my head, I plugged in this huge number. I plugged in like 10,000. Massive number. And I know if I square a massive number, it's going to be massive. And if I multiply it by this, well, that's like half of it, basically. It's still a huge number. And then if I take that 1,300 and subtract that huge number, it's going to be negative. I'm just showing you, like, that's the logic I use. But mechanically, just plug in 50, plug in 55, and you're there. All right, so we have a local max, right? Local max, where our revenue function, if we plug in 53.75. Now, we would have to actually plug that into what to figure out the maximum revenue? The first one, right? The local max, we plug it into here. So, I don't know. I have my phone, I'll do it. So keep in mind though, like, you know, in terms of the business, you can't have this, right? Like, you can't have a decimal demand. But for us, I mean, we would basically be saying like, okay, 53, 54. Somewhere in there, we're going to get the most revenue, right? So I'm plugging in 1,300, plugging this into the original function, times 53.75. minus 0.15 times I'm getting, see if anyone else gets this. I got 46,581.93. Anyone else get something close to that? No?
I got close to that.
Yeah?
I got that exactly.
Okay, good. And this is dollars because it's your revenue.
Yes, I said we talked about that.
Okay? So we will have a local maximum. Now, what about a local minimum? No, why? Yeah, look at your picture here. You never go down and back up, right? Never go down and back up. So you have no local minimum. What's that? Check it again. Redo it again. You should get that number.
So we put no solution for,
Well, there you would just say no local minimum.
okay.
Yep. So for you could just say no local minimum. Okay.
Oh, I forgot to plug in that.
All right. Does this this make sense? All right. Let me ask one more question on top of this one. Okay. Same problem. Same exact problem. Let me just ask one more thing here. So this is, I'm adding this to the questions. Is there a point of diminishing return? All right, so the point of diminishing return was something I talked about at the end of class last time.
Yeah, it's 53.75.
Is it? What is the point of diminishing return? What is it? It has to do with the second derivative, not the first, okay? So what we're looking for, I drew a graph of this. I'm going to leave that up there because I'm going to need that. What I showed you last class was that you could have a graph. Let's say you have revenue here. And say your revenue looks like this. Then your revenue is always going up, right? So here, we're saying it always is doing this. It's never doing that, right? But there's an important point right here, this one right here, where your graph goes from a smile to a frown, right? You'll see the frown right here, and you see the smile right here. It's like where the smile and the frown come together. That's the point of diminishing return, because what's happening is you have a positive change in revenue. It's going up, right? Revenue's going up. But then once you get to this point, I'm still going up, but look at the slope of the line is not as much, right? So that is the point of diminishing return. So what we're looking for is a change in concavity. Do you ever go from concave up to concave down anywhere? That's what this is asking you. Does your graph ever go from concave up to concave down? How do we know?
Because there's not a minimum, so it's just going up,
And then down, right?
yeah.
Okay, but this does not have anything to do with smiles or frowns. We have to look at the second derivative to be able to answer this. Okay? So anytime we're talking about concavity or inflection points or point of diminishing return, we have to look at the second derivative. Yes?
So the point of diminishing return, basically, like if the other side of it, the left side of the table thing, is like down or up, whatever.
Smile.
Yeah, and then it goes down the other side, then 53.75 would be. The
No, it'll be the point at which that happens, which is where the second derivative is 0. Okay? So this is actually not going to have anything to do with the answer to this question. All right? The answer to this question comes basically, it comes exactly from the second derivative and nowhere else. Okay? So let's take our second derivative. Well, I'm going to edit what I just said. It does have something to do with it, okay? But let's just take our second derivative. What is our second derivative? So that's 0, and then that's negative 0.90x. And then what are we supposed to do with that? Set it to 0? Yeah, and the only answer to that is 0, right? And if we put that on a number line, that breaks up our number line to two different things, right? So we can pick 2 test points, right? Now I'm going to pick them, even though we should not be doing this, but we'll talk about that in just a second. What am I supposed to plug those test points into? To the second derivative, right? So here's my second derivative. If I plug -1 right here, -1 times a negative number would be positive. So I'm going to be like this, right? And then here, plug in 1, I get negative, and that means I'm concave down, right? So does it look like I have a point of diminishing return? From the looks of it, does it look like I do? Do I go from concave up to concave down somewhere? Yes, but why is that not a point of diminishing return?
Not 0.
Because that's 0, right? It's at 0. And remember in the very beginning of the problem, we said x had to be between 0 and 70, which means look, this is our revenue function, right? We're saying that it's concave down, right, to the right of 0. So it's concave up and down. It's concave down, but it's going up, right? It's going up over here, and it's concave down. To the left of 0 doesn't exist. Why doesn't it exist over there? Well, x is negative, right? Negative demand, like what does that mean, right? So you can't, when you look at this, you have to take into consideration where you are in the graph. What if this would have said 10 instead of 0? Then we would have had a point of diminishing return, because 10 is within 0 to 70. So this is a little tricky, right? A little bit tricky. We almost met the requirements, but because of where it was, we can't call it a point of diminishing return. All right, let's proceed. We're actually jumping now quite a bit. We're going to jump to 12.5. We have almost reached the point where we're going to be doing a lot of applications. Are you asking me a question?
No.
Okay. Okay, 12.5. All right, we've been talking about finding the what maximum minimum?
Local.
Local, right? Local. Local only told us what was happening locally. Like I drew pictures like King of the Hill, right? You're just looking at the highest point on the graph in that little region. Now what we want to look at is seeing if we can't find the absolute maximum and absolute minimum of a function. That would be the highest point on the graph, on the entire graph, the highest point and then the lowest point on the graph, all right? This is a different question. For example, we could have a function like this, right? Let's say we have a function like that. That has lots of local maximums, right? We got local max, local max, local max, local max, local max, but we only have one absolute maximum, and that's up there, right? Same with the minimums. We have a bunch of local minimums, but there's only one one absolute minimum, and that's right there. So can we find those 2 points? The answer is yes, but we need one condition before we can do it. Okay, here's what we need. To be able to do this, to find the absolute max min, we must have a closed interval. Now, what do I mean by this? What do I mean by this? So let me give you an example. Let's say that we have a function f of x equals x to the fourth minus 8x squared plus 16. That function, if I graph it, does a whole lot of things. In fact, you know what? If this is on, let's graph it. Do you know how to turn the projector on, ma'am? Do you mind turning the projector on? Right behind you on that black panel, top left button, or actually the says top left says on off, top left, up one. Yeah, that one. You got it. And then on the light switches, the far left light switch, your other left. There you go. Turn the other one back. Nope, just the far left. That's good. Let's see what happens here. Y'all ready for Halloween? Did anybody do their Halloween parties this past weekend? Yeah? Were they good? Is that why everyone's tired? Pardon? I didn't hear you.
I went to go see the Halloween movie this weekend. Did you see it?
Oh, no, I don't know what Halloween. Oh, like Halloween, like the remake? Was it any good?
It was a remake. It was like a continuation, like a final. Supposed to continue.
Oh, I thought it was a remake of the original.
No.
No?
It was just like a conversation between the sister and Myers.
All right, so it's x to the fourth. Was it minus 8x squared?
Yes.
Plus 16. All right, there we go. So there's the graph. Ugh.
So if we were to use a computer online, could we easily just do this?
If you what?
If we were to go online, because I know it does with this, sir. If we were to just go online on a computer and type in the equations from our homework tonight, I guess.
No, I mean, you have to do this mechanically by hand. Yeah. Because on a test, you're not going to have a computer sitting there to graph these things. Yeah, I'll put that back up there. Yeah, I mean, you can use it to check your work, okay? All right, so this graph right here, it's implied by the picture, even though you can't really see it, that this just goes up forever and up forever, okay? Do you all see that? So we have a graph that looks like this, okay? And if I ask for the absolute maximum, you would tell me there is none, because both sides go up forever, right? If I ask you for an absolute minimum, is there an absolute minimum? Yeah, it does look like we have a lowest point on the graph. It looks like it happens in two different places, yes? Okay, so for us to talk about absolute maximum and absolute minimum, both, what you have to do is you have to cut the function off somewhere. You have to tell me, okay, I'm only allowed to look like between a certain place, and then just talk about that. So one place I could talk about right now is this problem. Let's talk about that function between -1 and 3. So if we take f of x equals x to the fourth minus 8x squared plus 16, and what did I say? -1 to 3. On the interval -1 to 3. Okay, so now I'm only allowed to look between -1 and 3, which is here, okay? I'm only allowed to look at the graph there. So I'm going to have the computer do that for me. So I'm only going to see how this works. -1 to 3. Yeah, that'll work. Can you all kind of tell what I've done there? I'm looking, no, that didn't work very good. I think that'll be okay. Just bring that down just a little bit so I can get to it. There we go. Okay, so if I'm only allowed to look between -1 and 3, then that means I'm only allowed to look, here's -1. I'm only allowed to look here till I get to 3, which is right there. Okay, so I'm only looking at that graph here instead of the whole thing. So when we say closed interval, what we mean is we give it a starting point and an ending point. If we can take a graph and just look at between a starting and an ending point, then all functions must have an absolute maximum and an absolute minimum there. They have to. So long as it's a nice continuous function that you can draw without picking up your pencil. So as long as it's a smooth curve, then you're going to have a highest and lowest point.
And that closed interval is only going to be x, right?
That's right. This is the restriction on our x values. This kind of makes sense? Okay, so how do we do it? It's actually a different process than what we just learned. So if you don't mind, could you turn all the lights back on and then press that on-off button again? We'll turn the graph off. Thank you. All right, so understand what this is asking? I mean, we have a function, we've restricted it. That's what the graph looks like. What is the highest point? So we're trying to find this point, right? And it looks like the absolute minimum is going to be here, right? So without the picture, how could we find these 2 points? So here's what we do. The steps for this are as follows. Find the critical points. What do I mean by that? What does that mean? Take the first derivative, set it to 0, right? So this is nothing new, right? Nothing new. Find the critical points. The second step for this, plug critical points into, let's say and endpoints into original function. That's it. There's only 2 steps to finding the absolute maximum minimum. So let me try and put this in perspective. If you have a function and you're trying to find the local maximums and minimums, you've got to do the derivative equal to 0, number line, test points. Those test points go into the derivative, right? If you're trying to find the absolute maximum and minimum of a function on a closed interval, it's a much easier process. All you do is find the critical points. After you do that, you plug those points and the endpoints. When I say endpoints, what am I referring to? These two, right? You take all those points and you plug them into the original function, all right? So what this is saying is, look, if we're going to have an absolute maximum, if it's going to happen somewhere, it's either going to be where the derivative is 0, so it's either going to be here or here, right? It could be those two, or it could possibly happen here or here. So what we do is we just figure out where these happen and then plug them into the function and compare them. The biggest answer we get is our max, the smallest we get is our min, and that's it. So there's no table, there's no up, down, none of that, okay? It's a cleaner process, I think. Let's do this one. Yeah, let's do it. So, first step, find the critical point. So I take the derivative. What's my derivative? So 4x cubed, right? 4x cubed minus 16x, and that's it, right? Set that equal to 0. How would you solve that? Ooh, this one's interesting.
First I would factor out 4x.
Factor out a 4x, okay. And what would that leave you with inside?
Then you'd be x squared minus 4.
X squared minus 4 would be inside. Everyone agree? Yeah? Anybody recognize x squared minus 4?
That's a full thingy.
That's a full thingy?
It's a plus and minus 2.
Okay, that's called difference of squares. So this is a difference of squares. This is 4x, and then this becomes two things, x plus 2x minus 2. Well, it came out eventually, right? All right, now what?
You just basically
Yeah, set them all equal to 0.
First one's automatically zero.
This one's automatically going to give you 0.
Would that always be the case, sir? Yeah. Right?
If it's a number times x, yes.
Negative 2 positive.
-2, +2. All right, now, these are our critical numbers. We don't need a number line this time, though. Not with this method. If we have a function on a closed interval, we do not have to use that method. Now, the next step, after we find the critical points, is to plug those critical points and the endpoints into the original function. So I'm going to have to plug 0 into this, -2 into this, 2 into this, and -1 into this, and 3 into this. So I'm going to have, what, 5 things to plug in? And I'm going to plug them in, I'm going to see what it spits out, and whatever the biggest number I get out is my max, absolute max, and whatever the smallest number is my absolute min. So I've got to do f of 0, f of -2, f of 2, f of -1, f of 3. There we go. So we only use the derivative just to get the critical numbers, and that's it, or the critical points. All right, let's do the easy one first. F of 0, 16, right? Just kills everything off except 16. All right, f of -2. -2 to the 4th power minus 8 times -2 squared plus 16 equals. What's -2 times -2 times -2 times -2? Positive 16. And then, let's see, we do this first. -2 squared, that's 4. But then times -8, so -32. And plus 16. That's 0. Okay. Now we plug in 2. What happens when we plug in 2? Same thing that we did when we got -2, right? Because when we plug 2 in here, it's the same as plugging -2 in, because it's to the 4th power. Same with that. So shouldn't we also get 0 there? Okay. How about f of -1? Let's see, -1 to the 4th power minus 8 times -1 squared plus 16. Let's see, what's -1 times -1 times -1 times -1? It's just 1. -1 squared is 1, so minus 8 plus 16. What is that? 9? One minus 8 is -7, then plus 16 is 9. And then finally 3. 3 to the 4th power minus 8 times 3 squared plus 16 equals, okay, 3 times 3 times 3 times 3 is 81. And then you have to do 3 squared first, so 9 times 8, 72. It's minus 72, and then plus 16.
So 9 plus 25.
So 25. Understand? What is the absolute maximum value of this function on this interval? 25 is the absolute maximum.
0 would be your min.
And the absolute minimum, it actually happens at 2 different places, doesn't it? But the value is actually just 0. So you're just plugging the numbers in and comparing them, right? The biggest number is your max and the smallest is your min.
So this is actually easier.
Yeah, I think so, right? Because no tables, no test points. Yeah. It's just find your critical numbers, plug those numbers and your endpoints. Just don't forget your endpoints, okay? Don't forget your endpoints, because if you forget those, you're going to miss, you could potentially miss the answer. Okay? That all right?
So, our just to restate, sir, is
You're what?
our endpoints are.
These are always given to you in these problems. They would be given to you. Yes. Yeah, you don't have to find them. The only thing you have to find are the critical numbers, or the critical points. Okay, I'm gonna start this next section. That's it for that section. You'll have to do your homework and do, you know, a couple of practice problems with that, but I think it's pretty straightforward. That's 12.5. That section was called absolute maximum minimum.
There's only 3 problems.
Yeah, there's only 3 problems. I'm going to start 12.6 though right now. So the problem I'm actually going to start with this is probably, if I were going to say, you know, out of this class, what I think is the most like useful and important like topic, this would be it. Optimization. All right? So we've got about 20 minutes or so here. 15, 20, 25 minutes. Oh, can someone start a sign-in sheet? Or you know what, I'll pass this around this time. Let's do it that way. We haven't signed in so long. I'm just going to black that out. Okay, we'll go around this way. I think it's the 29th, right? Okay. All right, optimization. So I'm going to give you a classic problem that we usually give students to start this off, all right, to get the whole idea going. Let's say that I'm a farmer, all right? And let's say that I have some different animals and I want to put them in these enclosures, all right? So I want to build these pens for my animals. And I want my pens to look like this. So I'm looking from the top. And I have, let's say I want to build 3 identical enclosures, right? So I'm looking from the top of this. Like if you wanted to do this 3-dimensionally, you could, you know, I don't expect you to be able to draw it, but like I have three enclosures. Does that make sense? Okay, so, but from the top, that's what it looks like. Let's say that when I build these enclosures, I'm going to build it so that everything here in blue is chain link fence. All right? And let's say that everything here in red is going to be solid wood fence. So I want my animals to be able to look out, but I don't want them to be messing with each other or getting each other all stressed out, so I keep them from looking at one another. That make sense? Yeah? Okay. Chain link fence up at my local hardware supplier costs me, and I'm totally making these numbers up because I don't buy chain link fence on a regular basis, all right? So I'm making this up. What would you say? How much per foot?
Per square foot?
Per linear foot. Let's say these are like, you know, 6 foot fences. They charge by the linear foot because they're in rolls.
About $10.
You want to go about 10? I was going to say about 10, 20. If we include the posts and we include the concrete, whatever. Can we just say 20 bucks?
Yeah.
$20 per foot, and that means linear feet. So like if this side right here is 3 feet long, it's going to cost me $60 for that foot, for that section. Agreed? Understand? Okay. And then what about the solid wood fence? You think that's going to be a little more expensive?
Yeah.
Yeah, probably. Yeah, let's say for this one, let's just go with 35. That's actually pretty expensive, but I'm using very, very exotic wood.
That's actually pretty accurate.
Okay, $30 per foot. Now this is installed prices, okay? This is for the guys who come out and dig the holes. That's how much they charge per foot. All right, got it? Now, as a farmer, I have some conditions on this, all right? My conditions are this. I need a total area. So I've got my whatever animals I'm going to put in here. So I have a condition. I want to give them a certain amount of space to live, right? So let's say that I'm going to give each of them 20 square feet. Okay? 20 square feet. Understand? So the total area must be what? If that has 20 square feet, 20 square feet, 20 foot, 60, right? 60 square feet. That's it. This is how much it costs me to build it, right? This is the cost if I use chain link versus solid. This is the total area. Let's say now I bring someone and I say, build this for me. What do you think the most important question is?
What's the cost?
What is the cost? Okay, yeah, sure. What's the cost, right?
How much of each? How much of each?
How much of each fence do I need, right? So let me ask you this. Do you think that there's only one way to build this? Or is there multiple ways to build this? There's multiple ways to build this. Let's just think about how could we get 60 square feet total. Now each of these pens has to be identical to one another, right? So here's one way we could do this. I'm not sure this would be very ethical for an animal, but we could do it this way. Couldn't we make each pen 10 feet long? I'm going to put 10 with the dash for 10 feet, right? Make each one of them 10 feet long. I should have done those in red, sorry. And then how wide would each of these pens have to be? 2 feet, right? This would have to be 2, 2, 2, right? So from here to here would have to be 2 feet, because that would be 10 times 2 would give you 20 here, right? And then another, this would be 2 again, 20, yes? Okay, so do y'all agree that this is one way I could build it? And that would cost me a certain amount of money, wouldn't it? Now, are there other ways I could build it? Okay, someone give me an example of another way I could build it, not using the same dimensions. You want to go 5 this time? So go 5 this way. And that means the inner pens would have to be wider, right? So they would have to be 4 and 4. So from here to here would be 4. Same with from here to here, 4. Same with from here to here, 4. Do we all agree with this? So this would be 20, 20, 20. It's not drawn to scale, sorry. And this one would also be 2, 2. Okay, and then we could continue, right? Like you could be really cruel. You could make it like 1 foot wide, and these little animals, I go down. They can walk 20 feet and then just turn around and just go back, right? So
Like this table, 80 square foot, it's almost like this table. If it was just like 2 foot longer, like
Yeah.
60 square feet.
yeah, it's not much.
Yeah.
They're little chickens or something, all right? Not elephants or anything.
Yeah, no, yeah.
That would be using a chain link fence anyway. Okay, so here's a question for you. These are 2 ways of many different ways I could do this, right? Is the cost the same either way? What do y'all think? I want your gut instinct. Is the cost of doing it this way the same as the cost of doing it this way?
No.
What is your gut telling you? No?
Wait, hold on.
Absolutely not, because you're using two different materials. So totally, you're gonna have 20 square feet of wood fence for the one that's 10 by 2, but I'm only gonna need 10 feet.
Let me simplify. You're on the right track. Let me simplify the problem. What if this was all chain link? Everything was chain link. Forget the wood. What if it was all chain link? Would it matter which way I do it? It actually turns out it does matter. It still matters. Okay? It matters. All right? We would have to go through, I'd have to show you examples, but it matters. The way you build it. Because look, if I did this crazy, look at this crazy, this is a crazy way of doing it, okay? Couldn't I go 40 feet, right? And go half a foot, right? Half a foot, half a foot, half a foot, something like that? Couldn't I do that? I know it's cruel, but this is half. So what would be the area